Hi everyone. So in this video I'm going to go over the practice midterm. The midterm is going to be 15 questions worth 15 points apiece, and you're going to do it during recitation. So it's only a 45-minute test. It's not a whole hour. So just be aware of that. The other thing is you are allowed a cheat sheet, and you definitely should bring a calculator. So that's basically that. Below in the link or in the description of this video, you'll find links to Lewis structures. So there's a more in-depth thing about Lewis structures you may or may not have seen before. Also, there is links to a blank copy of this exam and also a filled-in copy of this exam so that you can get the answers to this test. Finally, you'll find a time for each of the questions so that if you don't want to watch all the questions, which I'm guessing most of you don't, you can just click on the time and it'll take you directly to the question that is being asked. So without anything else, let's get right into it and I'll solve the first problem. So the first question says, what is the theoretical yield of CO2 in the following reaction if 4 grams of methane, CH4, is reacted with 7.1 grams of oxygen? And then we're given the balanced chemical equation. So we need to figure out how much carbon dioxide we can make if we use all of our methane. We need to figure out how much carbon dioxide we can make if we use all of our oxygen. And then whichever one is less is going to be the amount of carbon dioxide we make because that reagent will be gone. So here we want to start with grams of CH4. We want to convert that to moles of CH4, then to moles of CO2, and then finally to grams of CO2. So I'm going to do everything for CH4, then repeat everything for oxygen, and then that'll be the answer. So starting with 4.0 grams of CH4 times 1 mole of CH4, we look up the molar mass of carbon and 4 hydrogen, and then we find that that's 16.05 grams of CH4 times. Now we want to go from moles of CH4 to moles of CO2. We use a balanced chemical equation. There's 1 CH4. We put that on the bottom. So 1 mole of CH4 on the bottom. And on top, 1 mole of CO2. Then finally, we need to convert to grams of CO2. So carbon plus 2 oxygens on the periodic table, which is 44.01 grams of CO2 per mole of CO2. And I'm going to write the answer up here. When rounded to two significant figures, we get 11 grams of CO2. Now I'm going to repeat all this for oxygen. So for oxygen, we're going to start with grams of oxygen, converted to moles of oxygen, then to moles of CO2, and then finally to grams of CO2. So starting with, in this case, 7.1 grams of oxygen times, remember that oxygen is O2, so the molar mass is 32 grams of oxygen per mole of oxygen, times, now we use the balanced chemical equation to convert from moles of oxygen to moles of CO2. This time there's 2 moles of oxygen per 1 mole of CO2. And then finally, to grams of CO2, we put the 44.01 grams of CO2 on the top and the 1 mole of CO2 on the bottom. Notice the last step, we're going from moles of CO2 to grams of CO2, moles of CO2 to grams of CO2, and we use the same conversion factor in both cases. When we do that math, we get 4.9 grams of CO2. So what this means is that after we make 4.9 grams of CO2, we've used all 7.1 grams of oxygen. Said another way, we have no oxygen left. We can't possibly make 11 grams of CO2 if we don't have any oxygen left. So the answer here is 4.9 grams of CO2 as our theoretical yield. Question 2 says, how many grams of sodium sulfate should be used to make 100 milliliters of a 0.1 molar sodium sulfate solution? So recall that molarity is equal to moles of solute divided by liters of solution. So in this case, we don't need to use this actual formula, but we need to realize what we have. Well, we want to start with the 100 milliliters of sodium sulfate. So we want to do liters of Na2SO4 to moles of Na2SO4 to grams of Na2SO4. Don't forget that Na2SO4 is found by Na plus and SO4 2 minus. It'd be a good idea to put some common polyatomic ions on your cheat sheet. we cross the charges, and we find that we get Na2SO4 as the formula. So we don't want the volume in milliliters, we want it in liters, so we divide that by 1,000. So we start with 0.1000 liters of Na2SO4. Now we want to convert it to moles. Well, we use the molarity to convert it to moles. This is moles per liter, moles per 1 liter. So for every 1 liter of Na2SO4, it contains 0.100 moles of Na2SO4. Now we use the periodic table to find the molar mass of sodium sulfate. And it turns out that 1 mole of Na2SO4 on the bottom, so it'll cancel out, is equal to 142.04 grams of Na2SO4 on the top. And when you do that math, you get 1.42 grams of Na2SO4 required to make 100 milliliters of the 0.1 molar solution. Number 3 says, how many lone pairs are on the central atom in the best Lewis structure of SO2? So this is a review from last semester, like we did the first day. There's a video in the description below that goes over in detail how to do Lewis structures. But quickly, I'm going to do this one. So first thing we do, we count the valence electrons. We have 6 plus 2 times 6, which is 18 electrons, because both sulfur and oxygen are 6A nonmetals, so they all have 6 valence electrons. We put the least electronegative atom in the middle. We bond it to the 2 more electronegative atoms because there's 2 oxygens, and we fill in our lone pairs. I have now used 2, 4, 6, 8, 10, 12, 14, 16, or 8 around this oxygen and 8 around this oxygen, which is 16. So I've filled the octets of the outside atoms. Now I want to fill the octet of sulfur. When I do that, I put the lone pair here. That's all 18 electrons. I've still yet to fill the octet, so I may do this, and what I end up with is sulfur double bonded to an oxygen with 2 lone pairs now, still a lone pair, and we have an oxygen like this. Now I want to do formal charges. This oxygen wants 6 electrons around it because it's in 6A, and it has 1, 2, 3, 4, 5, 6, 7. It's got an extra electron. It's negative. Sulfur's in 6A, it wants 6. It has 1, 2, 3, 4, 5. It's positive. And this oxygen has 6 and wants 6 and has 1, 2, 3, 4, 5, 6. So it's neutral. How can I make this less formal charges? Like that. And what I end up with is this, which is the best Lewis structure of SO2. This is now neutral. This is now neutral. I basically put an electron around sulfur by making the double bond, going from positive to neutral. I took an electron away from oxygen by making the double bond, going from negative to neutral. And this is the best Lewis structure of SO2. Of course, this has 1 lone pair on the central atom. Do note you would have gotten this question correct for how many lone pairs there are, even if you drew this Lewis structure. However, if it asked how many double bonds there were, then that wouldn't work out. So it is good to just get in the habit of drawing the best Lewis structure. Number 4 says, how many of the following are substantially soluble in water? So here we need like, dissolves, like. And what this means is that polar and ionic solutes dissolve in polar solvents. Water is polar. So this is going to dissolve polar and ionic solutes. This also means nonpolar solutes dissolve in nonpolar solutes. Solvents, I meant to say. So nonpolar dissolves nonpolar, polar dissolves polar and ionic. Well, NaCl contains a metal. This is ionic, and we all know salt is soluble in water. C10H22, if it only contains carbon and hydrogen, it's nonpolar. So this is nonpolar, and therefore is not soluble. Here's an interesting one. We have C12H22O11. This could be sucrose, which is table sugar. Because this has a lot of oxygens, this is polar, and therefore it is soluble in water. This one is nonpolar for the same reason that C10H22. It only contains carbon and hydrogen, so this is nonpolar, so it's not soluble. So the answer here is 2 of these are soluble in water. All right, number 5 says, which of the following statements is a good hypothesis when someone observes that they can't find their cell phone? So we start with an observation. The hypothesis is an explanation for that observation. So the cell phone is black. That's probably not why it's lost. So that's not a good answer. The cell phone is lost. That's the observation. That's not a hypothesis. So that's probably not a good answer. The cell phone is probably in my room because that is where I last used it. This is a prediction. What did we predict? We predict that it's probably in the room. And there's a reason for that because that's where I last used it. So we have a prediction and a reason. That's a hypothesis. So that is our choice letter C. This question says, when excess HCl is reacted with 0.422 grams of magnesium metal, what is the mass of the gaseous product formed? Well, here we need to find the reaction. I'm going to write it down here because we're actually going to use it for question 8 as well. The reaction here is magnesium solid plus HCl, aqueous, dissolved in water, yields MgCl2, magnesium's 2 plus and Cl's minus, we cross the charges, aqueous, plus H2, hydrogen, not H2O, hydrogen gas. This is a reaction we did in the gas collection tube. To balance it, we need 2 Cl's and 2 H's, so we put a 2 in front of HCl. Now it's just a stoichiometry problem. So we want to go from grams of Mg to moles of Mg to moles of H2 to grams of H2. To do this, we start with 0.0422 grams of magnesium times 1 mole of magnesium. We look up the molar mass on the periodic table, and it's 24.31 grams of magnesium times, well, for every 1 magnesium, there's 1 hydrogen. So 1 mole of magnesium on the bottom, 1 mole of hydrogen on the top, times the molar mass of hydrogen is 2.02 because it's H2. So it's 1 mole of H2 on the bottom, 2.02 grams of H2 on the top. And when you do all that math, you find that there's 0.00351 grams of hydrogen. So that is choice letter B. It says, which of the following are true of 1 moles of an ideal gas at absolute zero? The pressure of the gas is 0. That is true. The mass of the gas is 0. Cooling something down doesn't change its mass. How much matter is in it? The moles of gas is 0. That doesn't make any sense. You have 1 mole of gas. 1 mole of gas doesn't turn into no gas. It doesn't disappear when you cool it down. And of course, all of the above can't be true because B and C are bad answers. So here the answer is choice letter A. Number 8 says, if 2.91 grams of magnesium is reacted with excess HCl and 301 milliliters of hydrogen gas is collected in a gas collection tube over water at 1 atmosphere of pressure at 25 degrees C and 1 atmosphere of pressure, what is the experimental molar mass of magnesium? And then it gives us the vapor pressure of water. This is exactly what you did in lab, but this is a hard question. So experimentally, the molar mass of, in this case, magnesium is the grams of magnesium divided by the moles of magnesium. So this is going to give us the molar mass. So we already have the grams here. We need to find moles. Well, to find moles, we have to use PV equals nRT. Specifically, we have to use N equals, divide both sides by RT, PV over RT. Now, to do this, we need to start with the pressure. Well, here we need to use Dalton's law of partial pressures. Lots of moving parts here, but basically what this ends up being is the pressure of hydrogen is equal to the pressure of the atmosphere minus the pressure of the water vapor. So the pressure of the atmosphere is 1 atmosphere, which is 760 torr. So it's 760 torr minus the pressure of the water vapor at this temperature, which is 23.8 torr, which is 736.2 torr. But in order to plug into PV equals nRT, we have to have this in atmospheres. So times 1 atmosphere over 760 torr, and we end up with 0.969 atmospheres. So That is basically now the pressure. We can plug that in. So we start with N equals 0.969 atmospheres times the volume, the 301 milliliters, the volume has to be in liters, so 0.301 liters. R is a constant, 0.08206, that's liter atmospheres per mole K. I'm not going to try to write that all out because I won't have space. Times the temperature in Kelvin. We have to convert this to Kelvin by adding 273, so this is 298 K, so we plug that in. Finally, we find that the moles of hydrogen is 0.0119 moles of hydrogen. Now, if we go back to the balanced chemical equation, this is not an oxygen, it's a mistake. So there's one hydrogen for every magnesium. So this is 0.0119 moles of hydrogen, which is also 0.0119 moles of magnesium. The reason they're the same is because in the balanced chemical equation, we have 1 to 1. So now we can finally plug in the grams, which is 0.291 grams, and the moles, 0.0119 moles, and we get the experimental molar mass, which is equal to 24.4 grams per mole, which is choice letter D. Question 9 says, when heating an Erlenmeyer flask in water on a hot plate and measuring the temperature and pressure, a student forgot to secure the stopper in the Erlenmeyer flask. The rest of the experiment was set up correctly. Which of the following will the student observe? So this is where we heated up the flask and we monitored the pressure and we tried to experimentally determine absolute zero in Celsius. So if you don't hold pressure in the flask, the pressure will remain constant the entire time. It'll essentially be the pressure of the atmosphere. The volume of the flask will not change if you forget to put the stopper on securely. The mass of the flask doesn't change because that doesn't have anything to do with the stopper. And the temperature doesn't remain constant because remember we put this into a warm water bath and we heated it up on a hot plate. So in this case, the pressure remains constant because it's leaking and we're simply reading atmospheric pressure around 1 atmosphere the entire time. Question 10 says, a student generated the graph below. What is the experimental value of absolute zero? Well, if we notice here, we have temperature in Celsius on the y-axis, and we have pressure in torr on the x-axis. So experimentally to determine absolute zero, the pressure has to equal 0. Well, when pressure equals 0, x is 0, and y equals b, said another way, the y-intercept. The y-intercept is the experimental value of absolute zero because it is the temperature at which the pressure is 0. So we're extrapolating this line back. Now the question is it minus 329 K or minus 329 degrees C? To answer that question, we simply look at the axis and we realize that it's minus 329 degrees C. Another way of doing that would be to realize that minus 329K is not possible, right? 0K is absolute zero. Question number 11 says, when potassium nitrate is dissolved in water, the solution cools. Which of the following statements is true? Well, if the solution gets colder, then this is endothermic. The heat of solution is endothermic. So delta H equals positive when it's endothermic. So the heat of solution is positive and endothermic. Number 12 says, what is the molality of a KF solution if 0.231 grams of KF are dissolved in 225 grams of water? So in this case, we're going to remember that molality is equal to moles of solute over kilograms of solvent. So in this case, what we want to do is we want to go from grams of KF to moles of KF using the molar mass, and then we want to divide by kilograms of water, which will give us the molality. So when we do that, we start with 0.231 grams of Kf times 1 mole of Kf on the top, and the molar mass of Kf is 58.10 grams of Kf on the bottom, times, to divide in dimensional analysis, we put a unitless 1 on the top, and then we put this in kilograms, divide by 1,000, 0.225 kilograms. So we put in 0.225 kilograms on the bottom, and when we do that math, we get 0.0177 molal, or because it gives it in scientific notation, we move it 2 times, so it's 1.77 times 10 to the minus 2 molal, which is choice letter C. Number 13. Between question 13 or question 8, these are the two arguably hardest questions on this problem set. So let's take a look at this. It says determine the freezing point of a solution that contains 78.8 grams of naphthalene, and it gives us the molar mass, in 722 milliliters of benzene. And it gives us the density of benzene. And then it gives us the pure benzene has a melting point of 5.5 degrees C and a freezing point depression constant of 4.90 degrees C per molal. So delta TF equals I KF M, where I is the Van Hoff factor, how many things it breaks up into in solution. This is covalent, so I equals 1. Kf is the freezing point depression constant, it's given. And M is the molality. If you're not sure how to calculate molality, see question 12. Because in question 12 I calculate the molality. I will calculate it again here. So we know I and Kf. What we don't know is M. So I'm going to move over here to molality, which equals moles of naphthalene divided by kilograms of benzene in this case. So what am I going to do? Well, I'm going to need to find moles in kilograms. So starting with naphthalene, I have 78.8 grams of naphthalene times 1 mole of naphthalene per, molar mass is given, 128.16 grams of naphthalene, which when I do the math gives me 0.615 moles of naphthalene. Now I need to figure out how many grams of benzene or kilograms of benzene I have, and I have the density. So if I start with 0.722 milliliters, 722 milliliters of benzene times, there are 0.877 grams of benzene per 1 milliliter, because this is grams per 1 milliliter. And when you do that math, you get 633 grams of benzene, which is 0.633 kilograms of benzene. So we get 0.633 kilograms of benzene. Now we can plug in. I have moles of naphthalene, 0.615 moles. I have kilograms of benzene, 0.633 kilograms. When I do that math, I get 0.971 molal as my molality. Now I can plug into my equation. Delta T equals I Kf times M. I is 1 times Kf, which is given in the problem, 4.90 degrees C per molal, times 0.971 molal. And what I find is that the freezing point depression is equal to 4.76 degrees C. Now be careful, because the question says determine the freezing point, not the freezing point depression. So therefore, I need to find the freezing point. The original freezing point is 5.50. It's going to go down by 4.76. These are both degrees C. And when I do that math, I get 0.74 degrees C as the new freezing point. In the past, you used water, and water has a freezing point of 0. So whatever the freezing point depression is also the freezing point because it happens to be that the freezing point is 0. On the midterm, we'd probably give you water, but this is a good question. If you can solve this question and you can solve question number 8, that's very good, and I would suggest practicing with these types of problems because it'll help you out a lot on the midterm on some of the more challenging questions. It's not to say you shouldn't do all the other questions too, because they're not all going to be like this, but that being said, they are helpful. Question 14 says, which of the following will have the lowest freezing point in when dissolved in water? So delta TF equals I KF M. If you notice here, they all have the same molality, so therefore, and they're in water, so they also have the same KF. So KFM is a constant. So the only difference is I. So we need to figure out what these things break up into in solution. Well, barium is a 2A metal, so it breaks up into Ba2 plus aqueous plus 2Cl minus aqueous. This is a colligative property. A colligative freezing point depression is a colligative property, and colligative properties do not depend on the amount of the identity of the substance, but only the amount that is present. Said another way, for colligative properties, this will have triple the effect because when barium chloride dissolves in water, it has 3 particles in solution, not just 1 particle in solution as if it were a covalent compound. So here I equals 3. 1 barium plus 2 chlorides. Lithium chloride breaks up into Li plus aqueous plus Cl minus aqueous, which is 2 things. I equals 2. Iron 3 chloride breaks up into Fe3 plus aqueous plus 3Cl minus aqueous, which is a total of 4 things because we have 1 iron and 3 chlorides, so I equals 4. And NaI breaks into Na plus aqueous plus I minus aqueous, which is 2 things, so I equals 2. So in this case, the one that's going to have the greatest freezing point depression is the one with the greatest I. When I equals 4, because this breaks up into 4 things, because freezing point depression is a colligative property, it doesn't matter if it's iron or barium or lithium or sodium or any of the anions as well. Therefore, the thing that breaks up into the most particles is going to have the greatest freezing point depression. Question 15 is very similar to question 14. So it says, which of the following reactions depicts calcium chloride dissolving in water? Well, we have Ca2 plus and Cl minus. We cross them, and we get CaCl2. When this is a solid, it will break up into Ca2 plus aqueous plus 2Cl minus aqueous. In the previous question, we were asked for the Van Hoff factor, so here it would be 3. In this case, to find the correct answer of what it breaks up into, it is choice letter D. Question 16 says, if a student has 2 millimolar times 10 to the 2 millimolar blue number 1 dye solution and needs 100 milliliters of 4.2 times 10 to the minus 4 molar blue dye solution, how much of the 2 millimolar solution should be added to a 100 milliliter volumetric flask? Well, I'm going to start with 2 millimolar being 2.0 times 10 to the minus 3 molar. I'm going to divide it by 1,000 because it's 1/1000th of a molar. Now I can simply use C1V1 equals C2V2. My initial concentration is 2 millimolar, which is 2 times 10 to the minus 3 molar. V1 is what I'm trying to figure out. I'm trying to make 4.2 times 10 to the minus 4 molar, and I'm trying to make 100 milliliters of that solution. When you do the math, you find that V1 is equal to 21 milliliters. So we'll take 21 milliliters of the 2 millimolar solution to make 100 milliliters of the 4.2 times 10 to the minus 4 molar solution. Question 17 says, a student measures the absorbance of a solution of red dye number 40. Which of the following are possible lambda max for the red dye? Well, there's 2 things you want to consider here. First of all, if something appears red, it absorbs green light. Everything is being hit by white light. If you have white light and you take out the green light, it will appear red. The second thing that you need is to realize that green light is somewhere around 500 nanometers. So you can see 400 to 700 and this visible spectrum. So these two pieces of information are very important. So you don't have to memorize them. I suggest you put them on your cheat sheet. So a possible absorbance for red dye number 40 is 500 nanometers. Again, they absorb their complementary color. So something that appears red absorbs green light. And then second is to know what is the wavelength of green light, which you can get from this spectrum. I just Googled this. So you can find this, or you can find it in your textbook, or you could pause the video and take a screenshot. Question 18 says, a student obtained the calibration curve for the absorbance of red dye versus the concentration of the red dye solution. If an unknown red dye solution has an absorbance of 0.38, what is its concentration? Well, absorbances are Y values. Concentrations are X values. So we need to plug in a Y value. So 0.38 equals 98022x plus 0.0042. When you do this, you first subtract the 0.0042 minus 0.0042, and we get 98022x equals, I have it here somewhere, 0.3758. Divide by 98022, divide by 98022, and we find that x equals 3.8 times 10 to the minus 6 molar, which is choice letter C. Number 19 says, which of the following explains why molecules absorb light? Well, this is because electrons move from lower energy levels to higher energy levels. So they're at lower energy states, a photon hits them, and they jump up. This is what causes an absorption. So in Gen Chem, we learned it for hydrogen. So these are atomic orbitals, and it's not exactly correct, but it's this kind of thing. So we have an electron here, it jumps up, that's an absorption. When you have an electron up here and it falls down, it'll emit a photon of light, and that's actually where light comes from, and that is called an emission. So choice letter A is an emission. These protons don't move from higher energy levels to lower energy levels. These two answers are just nonsense. So A is an emission and D is an absorption. Question number 20 says, what is the purpose of a monochromator in a spectrophotometer? A monochromator is like a prism in a mirror, or a diffraction grating in a mirror, and what it does is it breaks up white light into its component colors. I guess that's something you just have to memorize, but that is the job of a monochromator. I'd just like to thank you for watching the video. I hope you found it useful. Again, in the bottom in the description, you can find the individual questions and the times at which they're gone over so that you don't have to watch all the questions. Thanks for watching.